Hi, I'm Clarence. Um, Today we're going to be talking about using machine learning to fight online abuse and automation. This is some of the work that I did in the first 3 years of my career. About 1 year ago, I stopped doing this stuff. But I think it's interesting to share because a lot of the lessons that I learned over the past few years playing the cat and mouse game with attackers was an interesting experience. This is a book that I spent 1 year writing with a co-author. My co-author used to be the head of anti-abuse at LinkedIn. Now he's leading the efforts at Facebook fighting abuse. And previously, I was working in a company that dealt with anti-automation. In particular, we were helping companies to fight problems like account takeovers, scraping, credential stuffing, and also fake account creation. Um, I studied AI at Stanford. I did my bachelor's and master's there. And the reason why I started doing research in machine learning is because I wanted to find some reconciliation between my course of study and my work. So I started to do some research in my own time about how to use machine learning in security and also what are some of the vulnerabilities that machine learning algorithms, infrastructure systems, and the mode of thinking of data scientists, what are some of the problems that exist in this space. So I've been giving talks in conferences. I teach classes in conferences and in companies about how security teams can make use of data science in a more effective way, and also how to make use of the power of AI and machine learning to do better at what they're doing and to make their day-to-day more efficient. So feel free to check this out when you're free. Previously, in my last company, we saw about 50% of the entire internet traffic by transaction volume, and today I'll be sharing some lessons that I learned from the experience. So in particular, the online abuse and automation, I think there is some clarity needed here. What I mean by online abuse and automation is problems like fake account creation, hijacking accounts, scraping content, and of course, spam. Spam, I cluster together spam and phishing, any kind of content-based actions that will cause a degradation in experience of your users on your platform. I consider that to be online abuse and automation. So, a very traditional method that people use to fight online abuse is, of course, to do these two steps. The first thing is to stop the bleeding. I can block an IP address, of course. And then the second thing is very human driven. So if I have a security analyst that sees I've blocked 50 IP addresses over the last 1 minute, I can keep blocking IP addresses, but as long as the IP address manages to get 10 requests in, then he can send 100K requests using 10,000 IP addresses, which costs him maybe $5, $5 US. And so maybe I want to write a longer lasting rule that's based on some business logic, right? Something I know about my website, something I know about how long it takes to sign up for an account, how long it takes for me to, like what I must do in order to sign up for an account or to send this piece of spam to 10 users, right? So I do something like if the count of the last hour's IP is more than 10 and all of them are sign up events, then I block it. Okay, so obviously this is something that is very manual. It requires a human to go in and look at what's going on, spend maybe an hour, maybe 30 minutes understanding how to block this effectively, and then to write this rule and deploy it. Okay, so of course there are some problems with this approach. Everyone here may know about proxy lists or IP services. I think this is one that I use personally for some reasons, but there are many services that sell you IP addresses. And of course, you can think, okay, if you're using AWS IP addresses, maybe I will block all of the IP blocks of AWS instances. I block all the elastic IPs. But then, of course, you have services that sell you residential IPs. So if the IP addresses come from residential ISPs, if they come from routers that were overtaken by botnets and they're just selling you time, how do you actually block this effectively since real users might be coming from those same IP addresses someday? The very proactive approach to solving automation is that is this thing called captchas, right? I'm sure everyone has experienced captchas at least maybe daily, maybe once every 2 days. These are some funny examples of captchas, but the reality is not that far from this, right? Okay, if you try to solve these captchas, you may face some trouble. But the problem with captchas is that not only is it a problem for user experience, it's also easy to be solved, right? There's a lot of services that help people to solve captchas. The traditional captchas are overwhelmingly easily solved, right? You can use image recognition algorithms to solve even very complex looking characters in images. And if they cannot be solved by software, then there are fallback mechanisms that these services use. They forward it to a captcha solving farm in Vietnam and the Philippines, where they pay people 1 cent per captcha successfully solved, and they don't pay them until they successfully solve it. So you have a 100% solve rate, and basically, if they want to bypass this, all they have to do is to pay an extra 2 to 5 cents per request. Maybe it breaks their business model, maybe it does not. But for sure, it's getting cheaper and cheaper. As long as image recognition, as long as deep learning systems can recognize images better, then a lot of these systems can be trained to be bypassed. So why machine learning can help? The reason I looked into security and machine learning was partially because I want to find some reconciliation between what I studied and what I did at work. But also because when you walk around conference floors and security, especially security conferences, you see company after company claiming that they're using ML for something, right? To most people who are not familiar with data science, who are not familiar with machine learning, who are not familiar with AI, machine learning can seem like a magical thing that solves a problem, right? As long as you can train a human to do it, then theoretically you can also train an algorithm to solve the problem. And this is true in some contexts and less true in other contexts. But in particular, I think there are 3 big points why machine learning is helpful in these scenarios. The first thing is that the security actions in the past were always driven by rules, right? It's always binary. I block or don't block. I allow or don't allow. And syntactic signature matching fails whenever you have polymorphic adversaries. So whenever you're devising a rule to capture some activity or to characterize some activity, then it's always possible to find an instance of the example that bypasses this rule or this rule doesn't cover, right? Unless your rule is perfect, which is almost impossible, then it's always possible to find instances of examples that bypass these rules. Also, system complexity gets more and more exponentially larger, and web applications get more and more complex. Even web developers who build the application may not know about some ways that users can exploit to maybe get that new user sign up bonus, to maybe boost their search rankings on the e-commerce site, or to maybe send spam to a bunch of people, because the system is so complex, right? So as vulnerability classes explode in web applications, machine learning actually gives you the chance to not have to understand fully what is going on, but to look at the data and look at what your users are doing in your platform, and then to base your decisions and to base whatever decisions the system is making on whatever is really happening on the platform. So by looking at logs, by looking at what real users are doing, you can see certain patterns that a human may not be able to think of. The last thing is that pattern matching is one of machine learning's largest strengths, of course. When you are plotting a graph in Excel, a 2D chart, when you're plotting the best fit line, a human may not be able to do the perfect job, but then the algorithm will always be able to find the best fit line that minimizes the error between all of the points that lie on the upper and bottom of it. So the next thing is that web abuse is rampant because hackers are productizing their hacking tools. So just curious, who has seen an interface like this before? Okay, so maybe you haven't, but I'm sure you've heard of something like that. This is called Sentry MBA. This is one of the most popular cracking tools on the internet right now. You can find it not even on the dark web. You don't have to go through an onion link to find it. You can just look for sentry.mba forums, and you will see people selling configurations for this software, right? So this is a very simple Windows application. What it does is it takes in a list of username and passwords. The passwords can be hashed. It can be plain text passwords. And then what it does is that it allows someone to try out these username and passwords on different websites. And then based on your HTTP response code, it tells you whether this is successful or not. So if you bought 1 billion passwords leaked from, example, the Adobe leak a few years ago, and you wanted to find out, okay, how many of these username and passwords actually work on bankofamerica.com? Most people reuse their passwords. I don't know the exact number, but it ranges in the reports. Sorry, slowly, please. So it ranges from 30% to 80%. So 30% to 80% of people reuse their passwords across more than one website. So of course, if you buy 1 billion passwords and 0.1% happen to work on a bank, that's a lot of money. But not everybody knows how to write tools like this. So of course, the real hackers don't do it themselves. They write tools and sell these tools, and then they get the script kiddies to actually do this. So because this is becoming more and more easy for people to use, just like it's easier for people to use to do programming these days because high-level APIs and programming languages are becoming more and more accessible. Hacking is also becoming more and more accessible. Online abuse is also becoming more and more accessible. So the vast majority of today's talk, I'll be going through a bunch of ways to characterize activity by attackers done in online abuse and automation attacks. And why is this? It's because when people think about machine learning, they often think about algorithms and infrastructure and systems. But the most important thing you can do to enhance the efficacy of your system is actually to find new sources of data, to enhance your data in a way that can give you more insight into what your algorithm is actually doing. And so data quality is often the most limiting factor in systems, right? If I had a system that were able to detect fraud on my e-commerce website, I can play with different kinds of algorithms. I can use SVMs. I can use deep neural nets. I can use linear regression tomorrow. And I may see small percentage differences or small percentage improvements in whatever my model can do. But if, let's say, I find a new way to extract features from what users are actually doing or what their intent is on their site, then more likely than not, you're going to be able to see 5–10% improvements in your algorithm's performance. So traditional signals for characterizing web attacks have been used for ages, right? All the online platforms have some notion of username, email address, maybe some cookies attached to requests, and maybe some way to save user agents that people have used to log into their site in the past. And then maybe some way to enhance IP addresses to include things like GeoIP. You can find out your ISP, do a reverse lookup through many of the online databases that are free. So these are commonly used as entities for rate limiting or just outright blocking. However, we have seen that their effect is often temporary, right? Because it's easy to create new usernames, to use new IP addresses through proxies, to remove cookies through HTTP request libraries, to change user agents, to change cookie values, and to do all sorts of things to mask your true intent and identity. But today we'll be focusing on a slightly different way of looking at how to characterize which user is sitting behind the computer making the request. So this method is called fingerprinting. Fingerprinting is probably used by most advanced internet companies that have a motivation to fight fraud, whether it's financially driven or reputationally driven. But fingerprinting just means that you're trying to group together events by similarity, right? You're trying to find requests that are sent by one user or a group of users that have a similar intent, have a similar characteristic, that maybe they're the same actor, or maybe they're paid by the same boss, maybe they act in a certain way, or maybe they're doing something in a suspicious way, right? So the way that we characterize abuse can be seen as a kind of reverse Turing test, because we're sitting on one end of the system, and we're trying to guess if the person making the request is a robot or a human, and how is that dissimilar from the Turing test of old, right? So just note that fingerprinting can have very bad privacy implications as well, because most of the time fingerprinting, when you talk about fingerprinting, you're talking about ad platforms or e-commerce sites trying to detect who the user is so that they can serve them better ads and boost their conversion rates. But in this case, just take it that the rest of this talk is about trying to detect who the human is, not for the purpose of earning money from them, but for the purpose of trying to identify them so that if they happen to be a bad actor, you can identify signals that can be used to block their activity or to apply some action on them in some other way. Google Ads was the winner in the online ad marketplace, the real-time ad bidding marketplace since a long time ago. Of course, they had a lot of competitors at the time because it's such a lucrative marketplace, right? And they famously won the war because they did the best job at detecting when ad fraud was occurring. So whenever you ran some ads and you want to, for example, in a very simple case, you want to make your competitor pay more for something that they're not getting, for some benefit they're not getting. Let's say I had a competitor company B and they were running ads on Google ad platform. What I want to do is to make sure that they spend all their marketing budget and no real humans see their ads. So what I do is I run a botnet, I click on their ads 1,000 times, 1,000,000 times, and I run their marketing budget dry, pay per click, pay per impression, and no one real sees the ad, right? So of course, the ad platform cannot survive if they cannot block these attacks, because they will slowly start to lose reputation, and real people will not want to pay for their ads to be on here. And so the way that Google got the furthest with ad fraud was actually through this very simple method called HTTP header order. If you look at the two HTTP headers sent by request from Firefox 39 and Chrome 43, you'll see that there are some very subtle differences in the HTTP headers that come through on the other end, right? On the server side, you see HTTP headers, get, host, user agent, accept text HTML, etc. In Chrome, you see that the third one is actually connection, yeah? So this actually was found to be a pretty good way to do fingerprinting, and not fingerprinting of individuals, but fingerprinting of users or attackers trying to hide their activity by swapping user agents. So for example, if I were using HTTP request library in Python, I can change my user agent with one line, and then to the server side, to the enterprise, I can make myself be seen as maybe a Safari browser, but I'm actually still using my same Chrome browser, right? And if, let's say, I were Google Ads, I wanted to find out if this person was spoofing a user agent, then what I would do is to collect a whole bunch of user agents and HTTP header orders, and I do a mapping. And then I can see how likely this person is to be spoofing his user agent. And lo and behold, you see that there's actually a pretty interesting distribution of user agents and clients from UA. From the user agent, I can extract out the OS, the device, the browser version, the major version, minimum version, build release numbers. And all of these allow me to plot some kind of distribution over what are the likely HTTP header orders. And then if some new header order comes in for this browser that maybe I haven't seen before in this particular type of combination of browser version OS device, then it's likely not real. So I can just mark that as a higher likelihood to be fake. So this is super effective in detecting UA and device spoofing, and is one of the main methods that is still being used today, because to an attacker, if you want to spoof a large number of user agents, it's quite hard to do the research necessary and to keep up with the trends of new browser releases and to find what the correct HTTP header order is. Whereas for the platform, when you see 10 million requests a day, it's pretty trivial for you to build that database yourself, right? Just be careful that when using such methods, we have seen problems where CDNs or proxies or some clients, some devices, some phones have been known to randomly shuffle HTTP headers for some reason, then you'll start to block those people, which is not good. So whenever we detect an anomaly in this area, what we do is we just increase the reputation, we just decrease the reputation score, but we don't outrightly block them, right? This not being right does not mean that it's an attacker. It is a higher probability that this will be an attack. Okay. So this is something that a lot of people have also seen before. You can also fingerprint devices through the HTML5 Canvas API. Some of this is due to hardware manufacturing flaws or differences between physical graphic cards in devices, in phones, in laptops, in PCs. But when you render some graphics on the HTML5 Canvas API, then different devices will have slightly different rendering images. And if you just quickly compare the differences between devices, you get actually a very high precision fingerprint method. For example, if I render a font using a particular type of font typeface on Linux and OS X and Windows XP, different versions, you'll see quite different kinds of rendering. And of course, this can be used in a similar way to detect spoofing. When someone is trying to spoof something like a user agent is trying to spoof certain properties of the browser to bypass your rules, then this can be used to check if they're actually spoofing you. The next thing is font list, right? This is too small. You're not supposed to read it. But of course, if someone is launching attacks on a website, the most expensive things for them, besides humans, of course, is their infrastructure. So this infrastructure could be computers, could be virtual servers somewhere like EC2 instances, Azure servers. But what they want to do is to be able to use their infrastructure most effectively. And if you can break their business model by forcing them to change their infrastructure often, then a lot of the time it is effective. So one thing that enables you to view their infrastructure behind the characteristics that they're showing you, or they think they're showing you, is to look at their system fonts, right? System fonts are actually a pretty high entropy way of fingerprinting a browser or a client or a device. Most personal devices have some specific set of fonts on them. Some of them are customized, some of them appear in different order, and you can access the font list on the device through various APIs in JavaScript, in Flash, in Canvas. And this is a way that people have used very successfully to access font lists and to create a fingerprint that is high precision, right? And of course, there are some caveats here, right? A lot of the devices, let's say you're using a virtual machine that is pure Linux and you're not doing any kind of customization, you're not installing any software which changes system fonts, then you won't see much variation. But a lot of the time, the VMs that the attackers use, the AMIs that the attackers use are custom, and they spend a lot of time installing software that they have to use in order to launch these attacks, which is what enables us to characterize these using system fonts. Something that is also a bit of an implementation issue that we saw is that font lists are very large and are very long. So if you want to send this over to the server, if you want to do such detection on JavaScript, then it may add to a lot of network latency. You can of course hash this, but then when you hash it, you lose a lot of the information that you need in order to reconstruct whatever fonts is missing and how to attribute it to previously seen attacks, so on and so forth. So there are different solutions for it, but it's a small problem. Another thing is this one I think is one of the most surprising and kind of weird. WebRTC allows you sometimes to access the local IP address of your device. Behind the net, if you use this API, it allows you to get the local IP address of the machine. So something interesting that we saw in the past was that we see attacks coming from all over the world, right? The IP address maps to a geolocation that comes from Vietnam, from the Philippines, from Russia, from China. But when we do the WebRTC check on all of these devices, we see that, hey, how come all of the local IP addresses are sequential, right? It's all 192.168.0.1, 2, 3, 4, 5, 6, 7, 8. And then we can see that, hey, actually, they are doing a round robin of their user agents. And we can see that the user agent corresponds to the IP address, the local IP address number, and we can guess that this is definitely a botnet, or this is definitely a locally administered bunch of machines that maybe one person is running on his AWS environment and using a proxy server to access to attack these websites. And WebRTC gives you that insight into who is running these machines and what his local infrastructure looks like. In practice, this works about 2 to 3% of the time. So a lot of browsers, a lot of more modern browsers actually block access to this because it makes sense to. This one is very, very interesting. So the more traditional kind of audio fingerprinting is very intrusive. It requires you to play a sound on the on the speakers, and then have your microphone on device record it back. And of course, no one wants that to happen because you don't want your conversations to be heard by your phone. That's your worst nightmare. But audio context fingerprinting is something that goes one step less far, and actually allows you to fingerprint your hardware of your audio stuff in your devices. If it's a phone, then it's your sound card, and so it allows you to get some information about the sound card, a number of inputs, some latency information, and then allows you to plot this graph for every single device. So even if you have 2 MacBook Pros that were manufactured side by side on the manufacturing line, on the factory line, you'll see that they have different signatures, right? So this is pretty scary because if you are running one machine and you're running 5 VMs, all of them will have the same fingerprint. So you can tell when the different VMs are being run on the same machine, which is kind of, if you think about it, not that great for attackers. So this is a lot less intrusive than actually playing a sound and recording it back, but it's still very worrying for people who don't want their privacy to be leaked. This obviously, just like all of the other fingerprinting methods we saw previously, can be used to fingerprint people, can be used to fingerprint real non-attackers, and a lot of browsers are doing a lot of work to make sure that these accesses to these APIs are limited. The interesting thing is that many attackers don't use the newest browsers because newest browsers have some things that prevent too much malicious activity from going on, and also have some things that rate limit certain accesses to APIs that they need to automate in order to do things fast to drive down the operation costs. The last device fingerprinting piece is the battery API. This is, of course, pretty interesting. Many browsers now removed access. But if you look at the battery of a device, you can actually come up with some way of battery degradation, assuming that there's a battery in it, of course. If it's a PC, then there's no battery, of course. But if it's a mobile phone, many people who launch attacks on mobile apps, who make use of Charles proxy or some other mobile proxy in order to attack certain mobile APIs, they run mobile phone farms, right? And this is because it's so cheap to buy mobile devices, and it's pretty hard, like phone manufacturers, Apple, they make it pretty hard to spoof UUIDs these days. So it actually makes sense to run physical devices because it's economically sensible. But then, of course, when they're running real devices, you have real characteristics, you have real device properties that you can extract, and you can also group these together through simple clustering algorithms just by taking snapshots of different battery API information of every single request, and then trying to see which one is most likely to belong to the same device. Everyone has probably seen some version of this. Mouse movement patterns are one of the most standard methods to fingerprint users. But I don't want to focus on this stuff because this is pretty obvious. Like, it's pretty obvious that the one on the right is a automated bot, right? I can write a Selenium script or a Seculi X script in order to move the mouse in this straight way, and then click some buttons, copy Control-C, Control-V, and then try all the username and passwords, and maybe do some automation. But this is not interesting. I can do a lot of manual feature extraction and build a close to 100% classifier for all of this, and anyone can. But what we've seen is that the more you do this kind of stuff, the more the attackers are motivated to do very complex things. So for example, we've seen attackers do stuff like generate human-looking mouse movements through replay attacks. Okay, so this is not very advanced, because all they're doing is they have some people who are moving the mouse around all the time, and then they take small snippets of that, they offset it by some certain offset, and then they replay that in order to do the clicks that they need. And then we've also seen some that look very realistic, but everything else about the attack tells us that this is automated. So it means that they are using some kind of advanced algorithm to generate mouse movements that look organic, but it's actually not. So we can tell that obviously this is a bot, and of course the attackers can also tell that this is a bot. So they want to improve their algorithms, because most people, they have a strong incentive to bypass such defenses. So there's actually some code online that allows you to use LSTMs to generate human-looking mouse movements. And besides bypassing such systems, I'm not sure what those could be used for. Of course, you're looking at mouse movements. You have to look at keyboard, keystrokes, and touch patterns. This is a paper written by a previous colleague where she managed to cluster touch patterns on phones and do a user-by-user model, a predictive user-by-user model that can tell you how likely it is that this user is the user that he's claiming to be beyond his username and password, right? So you can see that the periodicity of each touch on each key on the phone can give you a pretty clear fingerprint as to how likely this user is to be user 2, user 1, or user 3. And of course, this can change as people use different devices. But the key here is that all these methods make sense because we're not using any one of them as a determining factor, right? All of these are combined together to create a score. And this score gives us a certain probability that this access made by this user, this login, is legitimate or is not legitimate. And then we can do some further action to double check or to request for a second factor authentication then. And lastly, we'll look at action sequence. This, of course, is not new at all. This was done by Silvertail, acquired by RSA some time ago. And you can as a website administrator, as an app administrator, you can see all your users' activities on your platform, and you can see what are the likely sequences of actions they do on your site. For example, if the eventual action is a login, then most likely they're going to start from the home page. They're going to go through maybe a sign-up process because they're not signed up, and then they're going to do the login. So you can actually build hidden Markov models like this, which is a very simplistic old kind of machine learning model, and you can build probabilistic graphs that show you how likely this access is to be a real human or a non-attacker, right? If I were trying to reduce my costs and I were trying to attack a website by signing up for lots of fake accounts so I can get the $4 coupon every time I sign up for an AliExpress account, what I will do is I won't bother going through the sign-up process. I go straight to the API. I use the mobile app API, and then I generate tokens in some way, and then I go straight there. But of course, if you're looking at sequence of actions, it's pretty rare that a real user goes straight to the API without without doing a GET request on the login page first. In fact, no real users should do that. So you can quickly come up with a reputation with a probability that this access is fake, right? Another enhancement that we tried and we thought was very useful was to measure time spent between each state change. So between each loading of the login page and each click of the post of the submit button, then you can come up with some model that tells you the anomalous score of each click. And of course, if I were an attacker and I knew they were doing something like that, I would call a random on it, right? I just do random delay between paste and submit. And of course, you can be fooled by that, But then actually, we tried several ways to detect that, and we found that most random algorithms in programming language libraries can be pretty easily characterized at scale. So if you see that one group of users using one set of proxy lists has a random distribution of delays, then you can see that all of them actually follow a pretty normal distribution, and no real users will have such a perfect normal distribution of delays between loading the login page and clicking. So even using random can you can find out what they're doing behind the scenes just by looking at large-scale patterns. So I still hear the translator going. Okay. So there are so many ways to fingerprint devices and browsers. The true challenge actually is not that we don't have enough sources of data, right? There are so many sources of data. We can do a very naive method of fingerprinting. We just concatenate all of these information together, and then we do a hash. That's our fingerprint. But of course, that doesn't work, because as long as the attacker changes one thing about the fingerprint, the entire hash changes, right? Of course, you can choose fewer features, but then that doesn't work either, because it doesn't give you enough entropy. So what you want to do is to find a perfect balance of features in order to create this perfect fingerprint that allows you to capture enough information about a single request, allows you to single out single attacker groups without accidentally including too many requests, without blocking real users in the meantime. So here are some quick tips that I learned over the last few years, where we played this cat and mouse game with attackers, and the quickest time that we saw an attacker bypass a fingerprint was 3 hours, and we don't know where they are, but likely not in the same time zone as us. And the longest time that a fingerprint lasted was about 1 month. So we see that running offline analysis of traffic and then creating a dynamic feature set just to throw attackers off is a very good way, it's a very effective way of balancing entropy and stability, right? If you can run offline analysis of the last 2 weeks of data and then create some set of features using clustering techniques, using very simple linear regression techniques to maximize your entropy, then you can create a different set of features each time, and then you can use this set of features to block attackers. Of course, this comes with complications, right? One common use of fingerprints is, of course, to characterize tools. You want to characterize tools like Sentry MBA, because you want to characterize tools like Phantom.js, you want to quantify tools like simple curl requests. Because all of these tools exhibit a very similar behavior, a very similar fingerprint. If you think about who's using these tools, the people that use these tools likely don't know too much about hacking, likely don't know too much about programming. And so they won't know to change the characteristics of these tools. And just by doing fingerprinting of these tools to detect Sentry MBA, to detect Phantom.js, you can do a pretty effective automation defense. The next thing is that we learned don't include raw features in any of the fingerprints, because raw features are the most valuable thing that you have, right? Even though we have so many sources of information, it is highly unlikely that you have an infinite source of ways to characterize users behind a browser. And so if you're going to run out of ways one day because all the attackers know exactly what you're looking for, they can do so by simple iteration and then looking at feedback. You will run out of features someday. So we never use raw features that can be modified. We use derivatives from features, and we use distributive methods. So for example, if I talk about the distribution of HTTP header orders across this country in this month, then if I see any kind of anomalies or if I see any kind of deviation from that, then that's something that an attacker can't trivially change, right? So some lessons learned and some things to talk about. Every time we're implementing a system like this, we think about the three types of problems, the three tools that we have in our back pocket. anomaly detection, supervised learning, and unsupervised learning. And of course, sometimes it's clear, sometimes it's unclear. If you have labeled data, if you have a lot of data, then you might want to use supervised learning. If you don't have any labels at all, it's too expensive to create labels, then use unsupervised. If you don't know what you're looking for, then use anomaly detection. But I want to talk a little bit about which of the problems we found to be the most useful, and these are things that may not be clear why this is useful using this method up front, and maybe even in retrospect it's not clear why it's useful, but it just happens to work well. Some of them I can find explanations for, some I cannot really find explanations for. But for example, if you look at distribution of device and browser type over a specific country, let's say if you look at the distribution of devices in China, most of the devices, mobile devices, maybe is Huawei ZTE. But then if you look at the distribution of Android devices in the US, most likely it's going to be Samsung or Google or some other phone that's popular there. If you see some deviation from that, that's an anomaly detection problem. Similar distribution of HTTP response codes. Most websites, if you use HTTP login mechanism, if it's a successful login, it's a 302. You do a redirect to your logged in account page. If it's unsuccessful, it's a 200 response. So if you see a lot of failures, then likely it may be an attacker launching a credential stuffing attack because most of his credential list will be invalid. The next thing is supervised learning is very useful if you have access to labeled mouse key touch event sequence behavior. User behavior is very well characterized in supervised learning because a lot of the time it's very quick to label. Like a human looking at a certain sequence of keystrokes or a certain type of mouse movement pattern can very quickly, in less than 1 second, guess if this is a human or a bot, right? So you can do this very cheaply, generate label data on Mechanical Turk for less than 1 cent a label. User behavior profile, fingerprinting can be done with supervised learning as well. Unsupervised learning is the most interesting one, I feel. If you want to do action sequence clustering or user event sequence clustering, then unsupervised learning happens to perform really well, especially if you have huge data sets. Of course, if you're trying to do clustering of raw signals on clients, then this happens to work very well as well because raw signals are harder to understand by humans, especially if you're looking at something like audio context, right? You're looking at font lists, then it's harder to know what the true behavior is or what the true device is, unless you're really an expert on every browser type, every client, every OS. But if you let ML do the sorting out of the data and then look at all the different sources and see where the largest differences occur, then you can often come up with ways to group devices together and then assign them cluster names that may or may not correspond to a real device, but at least you know that this cluster is likely to be from the same set of devices or same actor. And of course, the ideal production system is a multi-classifier system. It's kind of similar to an ensemble approach in ML, where we combine the detection of anomalies and the distribution properties, and then we use supervised learning to match incoming traffic, and then we use unsupervised learning to select features and to create new fingerprints that maximize entropy and balance also the stability of the fingerprint. I want to quickly go over a couple of things. Fake account registration, things that work well are using supervised learning to classify attacker tools, and also doing user behavior classification. I'll do a quick next one. Account takeover and credential stuffing. This is just a quick graph of what it looks like. The red stuff is what we decided to be automation. Around the middle is where we applied the detection stuff and we blocked all of the automated attacks. And we see that before we applied the defenses, most of the traffic is automation. And this is true for most websites, right? Most of the websites you see today, a lot of the traffic is actually non-human traffic. Some of them are malicious, some of them are not. This is not new information. The bot report every year by an anti-automation company in the US tells you this. But after applying the defenses using simple fingerprinting, we're able to reduce a lot of their traffic. And just by learning what automated tools look like using supervised learning, we can do that. Of course, false positives is a big issue, right? If you don't have enough entropy in fingerprints, you get a lot of false positives. If you do things like classifying HTTP headers and you get a bunch of signals that are maybe caused by CDNs like Akamai trying to randomly shuffle your header orders, then you get false positives. The important thing is just to constantly monitor so that if there are false positives, you know immediately. Cold start is an interesting issue that I want to quickly cover. If you have never seen this IP before, if you've never seen this ISP before, ASN, if you've never seen this country before even sometimes, then how do you access the risk and reputation of this access? So this is a paper written by my co-author at LinkedIn. That is a system that LinkedIn uses. Basically, if you haven't seen an IP address before, you do this. You go through this process of reputation propagation. It's a reverse traversal of the reputation tree. And this is because the core features like IP, like audio context, they can be used to create a multitude of other features, right? So if you haven't seen this IP address before, maybe you use the ISP's reputation as a way to generate a feature, as a way to generate a reputation for this IP. If you've never seen this ISP before, you use the country reputation to generate a reputation for the ISP and for the IP. So this is much better than traditional ways of doing missing data imputation on machine learning data sets, like using the mean or using the median, which don't really make sense in that context. The last thing that I want to go through is explainability. I think explainability, most people on ML, I think, agree that this is a big hurdle in most of the application of machine learning algorithms in critical contexts like security. If you can understand why a machine learning algorithm is making these decisions, then you can trust these algorithms much more easily. For example, if you look at the example of the dog, some of the more promising algorithms for explainability just create approximations of what these algorithms are doing under the hood. For example, on the right side of the image, you see the most important parts of the image in terms of pixel positions that the image classifier uses to do this classification. And of course, adversarial machine learning is a very hot area of research now. We haven't seen that much testing time tricking of machine learning models, but we have seen some very interesting attempts at trying to poison machine learning models, which is a very difficult thing to do from the attacker side. The last chapter of my book talks a little bit about this, but here's an example where if you see the 5 stars over here, this is attack traffic. And as you send more and more attack traffic, you see that one point which was previously classified as an attack is now classified as not an attack because the online learning model learns from incoming data and slowly shifts to adapt to this new traffic. So adversarial ML is an interesting problem because most of the machine learning algorithms, infrastructure, and principles about data science were not designed to capture characteristics of things that are actively trying to avoid being characterized. Right? If you think about image classification, no image is trying to actively avoid you recognizing it as a dog or a cat. Whereas most classification contexts in security, you're dealing with an actor that is actively trying to avoid you being successful. So in this sense, it's a very interesting paradigm because when you're dealing with adaptive adversaries that know what you're doing and can guess what they have to do to bypass whatever you're trying to do to characterize them, then it's a different problem altogether. Here are some resources. You can take a picture of it, or these are some classes, book resources that I used that I found useful over the past few years. We have an AI village at DEF CON. I'm organizing also a meetup group in the SF Bay Area in the US, and I live stream a lot of my meetups. Our last meetup was Facebook talking about election integrity and how they are fighting abuse especially in the freedom of speech area. Thank you.
クラレンス千代様、ありがとうございました。